I would like to introduce the fourth keynote chair, Mr. Syed Mukhalil, STMSC. Please welcome Mr. Syed Mukhalil, STMSC.
Tack MC. Hai allesammans. God morgen, Karsten.
God morgen. Det går veldig bra her.
Ja, jeg har fint. Jeg har det fint. Okay, I think since it's only us who speak Norse, we should speak English. First of all, I would like to introduce you to Karsten. Karsten is my professor at the University of Oslo. He is a leader of our research group in distributed infrastructure and security. In Simula research, he also the adjunct researcher. And he got his PhD from Darmstadt University in 2000. In the same year, he also joined the University of Oslo. In 2005 until 2018, he worked at the Simula Research Laboratory and become a member of ACM since 1996 and become the IEEE member since 2011. And what Karsten work, what his research interest is mostly in immersive multimedia system. So I want to tell you all that most of the keynote speaker before discuss mostly about the AI and everything else, and Karsten will talk a little bit different. His work is mostly with the low level. So without further ado, Karsten, I think it's your time to talk, please.
Thank you very much for the introduction, and thank you very much for the organizers of COSITE to have me. Yes, I'm going to try and share my slides. Let's see if PowerPoint is with me today. Yes, I would like to talk about a technology called device lending for sharing hardware resources over PCI Express networks. So as Dr. Hammam was already presenting, it's important for AI to be trustworthy and responsible, and national or even transnational orchestration is required for AI to use it responsibly. But in this talk, I would like to take a huge step back from the way in which we would use AI, and I'm talking a rather specific piece of technology that makes it easier and more affordable to develop, deploy, and use AI applications by sharing resources, and lots of other applications as well. This talk is based on material by Jonas Markussen. He was my PhD student, but he's also already an engineer at Dolphin Interconnect Solutions, who were so happy with his results that they employed him and use it now. The talk is going to start with a little motivation. Then I'm going to introduce to those of you who wouldn't know a bit about PCI Express. Take a quick look at a PCI Express technology that is pretty widespread, that is called non-transparent bridges. And then I will be able to talk about device lending and what it gives us. So if we today want to change workloads, we may either take our computers that we have in our house, in our lab, in our company, and if we need more computing power, we take out our old hardware and set in new hardware. Or maybe we are able to connect some external boxes, like in AI, we do frequently need a lot of computational power that comes from graphical processors. And we may have an eGPU box, and we can connect new hardware to our computer over an external link, Thunderbolt, a USB-C connection that is allowing these devices to just appear like built-in hardware via PCI Express. If the workloads get even greater, then we may have to go and develop our own huge clusters, or we're going to the cloud and rent our resources from these clusters. But developing for such a cluster environment is rather challenging because we need to understand how we use all these distributed resources. So it means we do have a cluster now, and in these clusters, different nodes all across them do offer us some resources. They have CPU resources for doing computation on normal CPU. They will usually have GPUs that we can use, and we need to find out on which of these nodes GPUs are available and how to make them accessible. And they may even have FPGAs, which we need to program directly and that need to be integrated into our application so that we can use them throughout the complete cluster. So we are always going to be logged into a single machine, and then we're going to have to make distributed computing work in order to use the resources that are huge and all over the place. So this means that we need to use the infrastructure that is very frequently based on Ethernet, sometimes the more performant converged Ethernet or InfiniBand or PCI Express networks, in order to get all these control, signaling, and data spread out over the entire cluster in order to perform our computations. And this kind of scale is required, in particular today when we have the training of AI networks to perform. Of course, there are lots of other applications. But in AI, we already know that every couple of steps in the training, we will have a step that is, for example, a fully connected layer. And then we have a gigantic data dependency that is going to cross over to all the nodes that we involve, and data needs to be exchanged between them. And that is usually rather slow and hard to develop. So we are usually then going to use some kind of middleware. So that is giving us a software abstraction that simplifies the use of resources and that allows us to make our life easier so that we don't need to program very low level and log into each of these machines remotely and deploy our own clusters. We have basically the same scenario as before, but the communication and the links and the topology of the cluster resources that we use, that is hidden from us. And we may instead develop software using a middleware layer such as RQDA, an open MPI version that is aware of CUDA, or maybe nowadays we use GPU direct RDMA implementations in order to distribute our data to these nodes and between these nodes as well. The key word here is that we use frameworks and libraries that are software abstractions that assist us in deploying this. And that is going to make our scenario quite different from what we had before. When we're in our lab and we have our own computer and we have connected additional hardware to it or maybe replaced some components, we are in this scenario that you see on the left in the local resource column. We have our application. We write our application directly using, in many cases, a CUDA library and some driver, and then it uses the hardware resources in our computer directly. And throughout the talk, I'm mostly going to refer to GPUs, but it can be disks, it can be FPGAs, it will be network cards in many cases. We need to find these resources and use them. And we are used at home, in our lab, in our company, to program directly for a small environment where we can make our initial tests. When we then want to scale up, we need to rewrite our software. We have our same application, but we need to integrate the middleware. This middleware needs to communicate with some kind of service on the computer. The service needs to provide an abstraction to the interconnection transport. Frequently, for large amounts of data, it is a transport that is using remote DMA in order to perform it, that's able to communicate over the interconnects to the other hosts, where we have the same layers again before we can finally reach the driver of the particular hardware card and the device itself. So we do have to do quite a bit of integration. We need to put this middleware into our applications, rewrite it, then we need to test it, debug it until we finally can run our applications. This introduces quite a bit of complexity, and sometimes this is even introducing quite a bit of performance overhead compared to the local device access, because we have a lot of steps of data conversion and control conversion when we are reaching from the application through the middleware to the protocols that need to be spoken over the interconnection network. But in PCI Express, we do have some other potential. You see, in PCI Express clusters, the same fabric that we use inside our own computer as a local bus to connect the CPU to the GPU in the same device is also the fabric that connects the computers inside this cluster. So essentially, we just have our own computer, and in this computer is one PCI Express card. It's connected to an external PCI Express cable that connects it to one or several of the remote machines, usually by means of a switch. And it is capable of extending the direct control that we have towards this other device. So on the right side here, you can see that you will usually have this interconnection adapter that takes up one of the slots in your computer, and it's then again connected via PCI Express bus to the PCI device. So our front-end node can essentially talk one protocol all the way from an application that is running on the front-end computer to the GPU or disk that is installed in a completely different node in the cluster. Always talking PCI Express without having the need to change protocols and, for example, involving user space applications to translate that to internet protocols for the transfer over the interconnection network. And that means that we can essentially end up in this situation where we do, of course, have an interconnection network between the node where our program runs and the node that we want to provide resources to us. But all of these abstraction layers, they are conceptually gone. We don't need to middleware. We can just use the application as it was when we developed it in our lab or company in the first place and make it remote. But that's, at this point, still a vision, right? So we were sitting together with partners from Dolphin Interconnect Solutions, and we learned from them how PCI Express external boxes work and how they can integrate into the local computer so that you can expand the capabilities of your local computer. And then I got this flash that because everything in PCI Express is memory mapped anyway, we are able to actually achieve the scenario that you see here on the left side. So what do we need to know about PCI Express to see how and why this really works? Well, the first thing is of course, that PCI Express is today an entirely dominant I/O bus technology inside computers. You do have a concept of bidirectional lanes that are configurations of either 1, 2, 4, and up to 16 lanes that are combined together into a link between a CPU and the device or among devices. And the amount of bandwidth that you can get out of these links is up to 16 gigabytes per second for PCI Generation 3, and PCI Express Generation 4 even gives you 31.5 gigabytes per second. And of course, there are lots of other interconnects, and Converged Ethernet and InfiniBand tend to compete yearly for who is the fastest. But PCI Express has the advantage that it requires no protocol translation at all, and we can just send the same packets from the CPU to the end device. Essentially, in PCI Express, we have this tiny protocol that is working pretty much like an internet protocol, but inside the computer and without the operating system being fully aware of it. And we are able to send data upstream from a device to memory that is inside the computer. We can send it downstream from memory attached to the CPU to a PCI Express device. And devices are also capable, if there is a switch in the system, to communicate directly by something called peer-to-peer, which is choosing the shortest path between devices that want to converge to translate data between each other. At the top of this is always the root, and the root tends to be close to the CPU of the computer, and that's why we call it the root complex. And whenever a computer starts, it will just go through all the devices that are included in the computer and enumerate them, and it's going to put all of their memory requirements into a gigantic local address space, which might have been a problem with older computers that gave us only an address space of 32 gigabyte. But nowadays with 64-bit addresses, we are capable of actually putting all of these devices into this address space and letting them be visible to each other. So of course, our operating system and our user space applications have memory requirements that are located somewhere in this 64-bit address space. We have interrupt vectors at some end, usually belonging to the memory that is seen by the CPU itself, and we have RAM that is located elsewhere. And then the devices have their individual memory requirements that they register to the BIOS at boot time, and they're going to get some blocks of memory inside the computer assigned to them. That's already a first little element. This kind of assignment of memory is a process of negotiation. The computer's BIOS is going to ask the card, how much memory do you need? How many blocks of memory do you need? And then it's going to give them addresses. So every PCI Express device is configurable and can understand different kinds of addresses. And now, of course, the CPU can see that in the address space, and it can send data directly to it, and it's going to be routed to the PCI Express device. And we call that direct writing memory mapped I/O or programmed I/O. But also devices can access the memory of the computer directly. So for example, they can perform direct memory access, and we are able to program that. So the device can find an address in the global address space and then transfer the data directly straight to the RAM that is connected to the CPU. And of course, when it's finished doing that, it also wants to notify the CPU that it has done its job. And for that, it raises an interrupt. And fantastically, in PCI Express, also these interrupts are memory mapped. So when the device is first configured, it will be given an address from the computer where it is allowed to write these messages that it has completed an operation. And these things are called message signals interrupt, or MSIX. And with all of these, we can now go ahead and transfer data in all directions and let data exist. For a GPU, that's fairly easy. For a disk, it's slightly more complicated. The disk needs to have notification when it's supposed to check a command. The driver needs to establish commands on behalf of an application. And the disk must also be capable of answering to the CPU when it's ready and has completed a transfer. And then commands can be rather complex, so they must be written into a command queue. This command queue is in the memory of the CPU, and the NVMe disk is told during enumeration where it can find these commands. So whenever a CPU wants the disk to do something, it puts a command into the command queue, then it raises a flag in the doorbell, which is mapped memory of the NVMe disk. The disk will be woken up. It figures out that it needs to read the command queue and perhaps perform a read operation by copying data into memory. That is, of course, then the CPU's memory. And when it's done with that, it raises an interrupt, again, by just writing to memory that the CPU is aware of. And we can do this again with networking cards. We can do that with FPGAs. We can do it with all kinds of devices. But the clue is, with these little things, the so-called non-transparent bridges, we can do that across multiple computers. And NTBs are things that you can buy as switches. NTBs can exist on PCI Express cards, or if you have some modern Intel Xeon chips, they can even exist inside the Xeon chip itself. So what we do, we need a card that is allowing us to put a PCI Express cable between our two computers, or two or more computers. And when you have done that, then these cards are, of course, enumerated during system startup. They're going to allocate an address space inside the global address space of the computer where they're located in. The computer on the other side is doing the same. Now, if the local computer writes to that address space it's going to be transferred over the network to the memory or some other local address space in the other computer. But because not every computer is located, has information located at the same data, the NTB is doing one more thing. It's translating the addresses for the computer dynamically while the packet is flowing from the one computer to the other without the CPU or the operating system needing to work on it at all. Now, using these NTBs, we can also make a global address space where every computer can export some of its ranges, including the hardware, and the other computer can look into it, have a window into the global address space, and then, for example, directly address machines, devices elsewhere in the network. And that gives us the possibility to use device lending, which is our idea that we offer. We call one computer the lender and the other the borrower. And if we now want to use the physical device that exists in our lender, then we can set up a mapping on the NTB of the borrower that translates the space in memory where the physical device exists on the lender machine and finds some space in the borrower. As soon as that happens, the operating system can be notified and it will get a hot plug event that tells the borrower computer that, oh, there is a new graphics card. Let me load the driver. The driver will be loaded. The driver is looking at the hot plugged virtual GPU that is not physically there. It's going to try to configure it, and that goes straight over the network to the other computer, where it's going to be configured and get information about where to write data, where to read data, and where interrupts are supposed to be. Of course, if you have a cheap card like a GTX GPU, the lender will at that moment have to stop using it. But if you have a modern GPU like a Quadro card, you can actually use SRIOV, and both computers can continue using it with different configurations. If we also want to use it, we do, of course, have this trouble that we need to be able to raise interrupts in the other direction. And in order to perform DMAs, we have the same issue. In this case, we need to perform a double mapping. We need to understand where our borrower expects data to reside, and we need to understand where the physical device wants to write. And then we need to make a transition from where the card intends to write into a memory space that these two adapters know. And from this adapter, we need to map the address into the memory where it's supposed to go. Yes. If we're now able to do this, then we have actually the scenario where for the application, this looks exactly the same in the local device as in the remote device. And we can use the remote GPU with our unmodified application in the local computer as if it was as if we had physically taken it out of one computer and plugged it into the local one. Compare this to the scenario that we usually are working on, and the whole application development and deployment process gets incredibly much quicker and faster. And even so, for the operating system, it is easier because the operating system is only concerned with the mapping at the initial stage. And as soon as the computer's addresses are all mapped, as the GPU device is completely mapped, we can use it as if it's a local computer. And we even keep exactly the same performance if the computer contains the GPU itself, or if the GPU is located on another computer and just mapped to us. That is true for reads and for writes, and gives us a lot of opportunities. And then we can even consider all the devices that we have in our lab, in our pool, in our company, as one pool of devices that each of the computers can dynamically loan when it has the job to do. And they may communicate directly with each other without any overhead. And they can lend and loan at the same time without any limitations. And when they're done, they can just return these tasks back to the global pool. So what is the big benefit? It is, of course, that developing becomes much easier than actually having to develop for multiple devices. An administrator and a programmer become different roles. A programmer doesn't have to understand everything. And you can even have more features nowadays than I was showing here. With that, I would like to conclude my brief introduction to device lending, and I hope that you find it beneficial. We have written a few papers through the years, and you can see them on these slides. Thank you very much.
Thank you, Carsten. I believe there is one or two questions maybe from the audience, or maybe what you have said is really confusing them.
I have a question.
Yes, please.
Okay. Thank you very much, Professor Karsten, for the very interesting topic. So I already read your corresponding papers, and because my expertise on image classification task, and as I see on the subsection that using the device lending, you also applied this on the image classification workload using Keras and the deep learning. So however, I only see the single task. I'm curious whether you or your research group also run another task, for example, maybe like face recognition and so on, by also utilizing the device lending probably. So I'm just curious about that. Thank you very much.
Yeah, so of course we've also used it in other contexts. We've used it for just image transformation, for real-time streaming. But we have, for example, used it in a hospital in Norway, where we're supporting live recognition of polyps during endoscopic investigation of the intestine. And the doctors are not willing to let just any kind of new device into the operating theater. So they have just the local small computer in there that's not supposed to make extra noise. It's noisy enough. So the actual computer is in another room, and we have a PCI Express cable to this other room, and the live annotation by doing feature recognition and feature extraction of the polyps is going to be performed on the hardware in the other room, but presented in the local one. So that's, for example, one very practical application that we've used it for. It has been trained offline. So this is during the use, not during the training.
Okay, got it. I got it. Thank you very much, Professor.
Thank you.
Yes, maybe any other questions?
Yes, I have one.
Okay, please go on.
Yeah, Professor. Thank you, Professor Greenwoods. My name is Rudy Kurniawan, and currently we are doing research with the how to say the room for isolation of the COVID. So we have a real-time system. We use like a back-off automation based on EtherCAT, that is Ethernet-based control automation. So now we would like to use image like a pattern recognition, image recognition, something like that with the artificial intelligence. And according to my experience, when we talk about the artificial intelligence, that means we need a very good computer for the computing and so on. But on other hand, we have a real-time system with a frequency of 1 kilohertz. 1 kilohertz or 2 kilohertz, very slow, but that is real time. That means the cycles must be exact all the time. So my question is, do you have maybe a suggestion based on your research to have like interface between two systems? I'm thinking about the two parallel system, one for the image processing and so on, and the result will be sent to our real-time system. So will your research with this peripheral can somehow be applied in our research for image recognition and artificial intelligence?
Yeah, so there is one particular card. So we're working with Dolphin Interconnection Solutions on this particular way of communicating. And I know that Dolphin Interconnect Solutions has drivers and cards for a few real-time systems. And as soon as they have drivers, it would be possible to offload workload in the same way. So I think they support RTOS and they support real-time Linux at this point. So it should be possible to use it. It's as long as you can have a PCI Express card in your real-time system, it would be feasible.
Okay. Yeah, we have a normal PC industrial with all the like other normal PC has. So
Yes.
yeah, maybe we should have more intense communication, I think, for this topic, but I see a good potential to be applied in our research.
I think if it's possible in the concrete case, we should talk a bit more. But it's definitely possible that it can be done even with the cards and the software that exists today.
Yeah. Okay, that was my question.
Thank you very much.
Thank you, Dr. Rudy. And I think this is the last question from Mr. Yuda. Please, Mr. Yuda.
Okay, thank you. Guten Morgen, Herr Professor Grivut.
Schönen guten Morgen.
Ja, es gibt eine sehr interessante Präsentation. Und, Entschuldige, okay. So, because you are from, Sie kommen aus Deutschland, deswegen,
ja,
ich habe eine Deutsche sprechen. So, I would like to ask from the security perspective, because it's kind of like you override the memory in this with using the PCI Express. Is it not by using this kind of NVM this or with the Dolphin itself, it can create a vulnerability in the system because you are kind of bypassing the OS and just use the memory from using the device.
Well, the thing is, you need an administrator to create the mappings, right? So if it may be even safer than a general application that uses RDMA, because RDMA needs to be programmed by every developer. Whereas this one here allows, if you trust your developers to write local applications and you trust your administrator to be responsible and not expose memories that are not supposed to be translated, you limit the security problem to a single person. So it may even be beneficial. Since the mapping is manual, well, so far it's very manual, but Dolphin is working on making it elegant. You reduce the danger.
Okay, so maybe one of the solution is kind of to make it isolate a little bit about the system. You can use the resource, but not to expose too much about this to the internet or.
Yes.
access.
So you're explicitly mapping, you have the NTB memory ranges, and then you're explicitly choosing the addresses that should be mapped. And that's the super user, an administrator who does that. So it is not more dangerous. Of course, I mean, you can imagine somebody putting a box, a snooping box into the PCI Express network. But I mean, if somebody is there, you are in big trouble anyway.
Interesting. Okay, thank you very much, Professor Trisut.
Thank you very much.
Thank you. Carsten, in the name of committee, I would like to say thank you very much for your talk. So we here realize that there is thing called like a device landing that we can use other PCs resources without even bother the operating system level. And I think that's all from us. And I would like to return the screen to the MC. Tack för idag, Carsten.
Thank you very much. Enjoy the rest of the conference. I'm going to stay around. I find it definitely very, very, very interesting so far. Thank you.
Excellent.
Danke sehr.
So I will return everything to the MC.
Thank you, Mr. Said Mukhalil, STMSC. And thank you very much. I would like to say for all the session chair and our keynote speakers, the certificates has been provided and will be delivered through the official email. I would like to say thank you for Professor Ashraf Zulkifli from University Kebangsaan Malaysia. For Mr. Professor Ashraf, please open the camera. Thank you. And I would like to say thank you for Professor Ng Ying Kui from Nanyang Technological University, Singapore. I would like to say thank you for Professor Karsten Griewitz from University of Oslo, Norway. For Professor Karsten Griewitz, please open up the camera.
Oh, yes. Thank you very much.
Thank you very much. Now I would like to say thank you for our keynote speakers, Dr. Hamam Riza, Key Expert Engineer of Technology, Information and Electronics. Once again, thank you very much for all of our keynote chairs and keynote speakers. And now we will move on to the photo session with all of the participants. For our keynote speakers and keynote chair, please stay in the Zoom room for a moment. We are now going to have the photo session, and for all participants, please open up the camera. Now we would like to take the photo for the first page. So the same direction will go until the 6th page. I'm going to count until 3. 1. Okay, maybe we're just gonna wait a minute. Kindly reminder for all participants to open up the camera because we are now going to have the photo session. Now, we would like to take the photo for the first page. I'm going to count until 3. 1, 2, 3. Thank you very much. And now move on to the second page. I'm going to count until 3 again. 1, 2, 3. Thank you. And then move on to the third page. I'm going to count until 3. 1, 2, 3. Thank you. And then move on to the fourth page. I'm going to count until 3 again. 1, 2, 3. Thank you. And then move on to the fifth page. I'm going to count until 3 again. 1, 2, 3. Thank you. And now for the sixth page, our last page, I'm going to count until 3. 1, 2, 3. Thank you very much for all the participants. And once again, thank you for all session chairs and keynote speakers. Kindly be informed the first parallel will start at 2 p.m. Jakarta time, right after the lunch break. The parallel session will be divided into 5 rooms, and further information will be described in the slide. Thank you.